Good morning, everyone, and welcome to the ELIXIR Czech Republic Friday Coffee, which is a seminar for the users of the infrastructure. This time, I'm pleased to introduce the tool or database, which is coming from Institute of Biotechnology, where they created the database dealing with assignment of DNA and RNA conformers under the guidance of Jiří Černý and Bohna Schneider. And we'll see in the next 20-25 minutes how you can use this tool, and which will be probably helpful in your work. So Jiří, please, the floor is yours.
Yeah, so good morning and thank you for the introduction. So as you already heard and read and seen, today I'm going to talk about our web service DNATCO in the public version 3.2, and also I'll show you the next one. So DNATCO provides tools for annotation, validation, refinement, and modeling of nucleic acids. It assigns the conformations in both DNA and RNA using a consistent description, so it doesn't really care if the molecule is DNA, RNA, hybrid, whatever. If it is a nucleic acid, it can work with it. So as I said, the current official public version of DNATCO is the version 3.2, but we will soon release an updated version. The web server is available at the DNATCO.datmos.org address. The datmos.org stands for the database of molecular structures. The older domain DNATCO.org still works, but only as a redirect to the new Datmos domain. So obviously, as expected here, DNATCO is supported by Czech ELIXIR, and it's, as also recorded, is at one of the services and datasets provided by our node from the Institute of Biotechnology. So on the page, you probably see the browser, I hope. So on top of the page, there are some tabs or buttons. So we are now on the home page. You can go to the help, which summarizes some basic features of the server and some prerequisites of structures. It should follow at least some decent format of the files and so on. In the tutorial section, it's quite small, but the main feature of it is it points to the latest Acta Crystallographica D paper, which describes this version in quite a big detail. So another tab which might be or even should be important is the table of conformers, which summarizes the values of the 12 parameters we are using for definition of each conformer, and we call the conformer NTC for nucleotide conformer. And we also introduced something called CANA, which stands for the conformation alphabet of nucleic acids. So it's like, because we have 96 conformers, and it's a bit too many to use it, say, for like sequence-like alignments and so on. So we defined, or also for graphical representations, we defined a bit smaller. Now it has like 14 or 15 letters of this structural alphabet of nucleic acids. Here you can also have a look at the actual fragment, because these 12 parameters are measured from like the atomic coordinates, but not as their Cartesian coordinates, but as mostly torsions and few like two distances. And the green atoms are the important 18 atoms we are using for measuring these parameters. So the next tab is like, it's called Browse Conformers, and it allows browsing of conformers. There is a database behind, like simple database and you can choose which conformation you want to search for, either in non-redundant or all PDB structures, and include or not like large structures, which is not so good idea in this older version. In the new one, it works fine. And it, like, you click submit, and depending whether you are looking for none or all structures, it takes a few seconds or a few more seconds, and then it loads in the results page, and you can see the actual browse, the search results in the browse tab, which we will see in a minute. So then there is a about tab, which summarizes the features and changes across versions, because it's already a few years we are developing that, so we are introducing new features. Well, you can obviously also read the relevant papers and download the underlying data, the definition of the conformers in Cartesian space or in the as these 12 parameters. And there are also like example scripts for programmatic access to DNATCO. So you can from Python you can upload PDB or ZIP file and or torsions and so on. Just like interact with the server, not only as a living user, but using a script. So if we go back to the home page, a user can basically either upload structure coordinates in PDB or MMSIF formats, or type PDB ID into the box and choose either structure from RCSB PDB or PDB redo. And after submitting it, it will show the for these already deposited structure, the pre-calculated data and pre-calculated results. So now I'll basically switch to the next version, which at least at the homepage looks quite similar. So both the 3.2 and the next one, they internally use the MMSIF format. So even if somebody uploads a PDB, it's internally checked for consistency, and if some information is missing, it's added by a Maxit program, which was kindly provided by the authors from the RCSB PDB. And user can also like add optional experimental data in now not only as a CCP format, but also as structure factors in SFSAFE or MTZ or the previously already supported CCP4 or MRC formatted maps. These maps are like temporarily stored for like right now it's like for 7 days and then it's deleted, so we don't keep it forever. So we keep the original form, and then it's also converted to the format used by the density server, this part of Molestar package you heard about last week. So it's not big surprise that we are also now using Molestar for the graphical representation of the results. And the necessary extension of Molestar was developed mostly by my postdoc Michal Malý, who obviously discussed that with David and Alex, the main authors of Molestar. So if we enter a PDB ID, or in this case just simply click the example 1 DNA, it will show us the result page, which contains actually quite a lot of information. So if we start from here, you can see the title of the structure as a link to the RCSB PDB, and then some summary of like our analysis, how many steps we detected, how many models are in the structure. The results can be downloaded as CSV or JSON file. there are these numbers of steps within RMSD groups. So obviously green is good, red is not so good. So if you have a lot of green ones, it's fine because you are within like half an angstrom from the reference. And then there are like two additional important information. One is the average conform, which the conform is a conformer validation score, which ranges from 0 for like outliers to 100 for perfect agreement to the reference. And it's calculated somehow. It's described in the papers, obviously. And because we can calculate this value like per structure, we can also compare it to the rest of the PDB. So it also gives you some percentile with respect to the rest of the PDB. And these two, or like the conval and the percentile and these groups are also like graphically represented here. Here it's boring because you have only green, because this is actually quite a good structure. So below you can see a table which summarizes the information like per step information. This is like for the whole structure, so we can now go into the details. It's clickable, so you can sort it by, for example, conval here from the best or in the reverse direction to identify either the nicest or like some potentially problematic steps in order to like try to improve them. Well, obviously it doesn't make much sense in already deposited structure, but at the end of the presentation I'll show you like live data before deposition to PDB. So here will be the details. With the table obviously summarizes some code of the step, the alphabet letter, the NTC, conval, and RMSD, and it's also color coded. In this one, as I said, it's quite good. So on the left, bottom left, you can see the structure, and the conformations of the steps are like color coded and plotted as these colored pyramids. And obviously there is like key for these colors, so you can immediately see that because it's mostly blue, it's mostly B information of the DNA, but it's not completely blue. So actually, contrary to the common belief, 1-DNA is the dodecamer is not the ideal B1 canonical B1 form, but it's a bit more complex. There are some other B conformers as well as a few A-like conformations. So even this like structure as simple as this can be in fact quite complex. The size of these pyramids is also corresponding to the conval value. So the bigger, the better. Maybe I already showed that if you hover over the step or over the pyramid, it also shows the summary information, the NTC and the scores in this window below. When I move the cursor, it disappears. But, so it's like the information is like shouting on you from different places. So if you click a step in the all-star or in the table, it shows even more information, and it's the superposition of the reference conformation on the central step in green. I hope it's visible. And also the overlapping previous and next steps here in blue and cyan. And you can immediately see that there are some, it doesn't fit perfectly, so there are like possibly some ways how to improve it. So for like if you want to play with it more, there is this settings tab where we can like turn on display of waters and protein or like other molecules. There are no, so it doesn't make sense to click it here. So we can also switch graphic representation from cartoon to sticks. We can make the pyramids transparent so you can see the actual phosphates. You can turn on and off the pyramids and then play with their colors. So now B is green. And we can go even farther to the level of like, because this is grouped somehow, and then we can really pick a given conformation, a given conformer. So we can, for example, select only this BA05 conformation, and we'll see where it is in the structure. For this small structure, it's probably not so great representation, but if we are looking at ribosome, which is a bit bigger, then these spheres are actually quite useful because you can immediately see the like scaffolding A helices, like mostly boring. If I over exaggerated a bit, and then there are like scattered different colors, like the red open conformers, the green Z conformers, and so on. So in this really simplified representation, you can immediately pick the important or interesting parts of the structure. So you can also turn on the Restraints Modes, which I will actually show on a different structure. So if the Restraints Mode is activated, it extends the results table. You can see that there is like additional column and some other controls, and it's actually it helps you to keep track and like save different settings. Like if you look at this step, the overlay, this green reference is kind of sticking away. It's not overlapping perfectly. So you can actually go into this similar tab, and there are two plots in there, which like the top one summarizes, it's a scatter plot of Cartesian RMSD versus Euclidean distance for all 96 possibilities. And it's again, as you see, color coded. So if we go into this like similar region, the system detected that it's most similar to AA00, the canonical most common A form. But actually, this there are some alternative conformations, and if we click it, you can actually see that the fit, like the overlap improved, the fit is actually reasonably similar to the AA00, and also the connectivity, the plot below improved. So it shows that the previous open step is actually reasonably close, as well as the following AA00 step. So by like clicking these points, it kind of recalculates itself. It shows how well a conformation fits into the structure. Obviously, this one doesn't. And if you decide that this might be the right solution, you will see it here in like so this is modified, so it's in red, and you can save this restraint set and download it. It's for FMAC, Phoenix, and MMB macromolecule builder to like the first two for refinement of the structure, the MMB for like improving the structure density fitting, or even like de novo modeling. Obviously, as I said, for deposited structures, this is a nice exercise, but probably it will be more useful for people like already still solving their structures, and this is an example of that, where we have a structure which is solved by a group of Paulina Řezačová at IOCB, and Markéta is actually she found that DNATCO can be useful, and she is trying to improve the structure on like using our tools, and it also motivated us to introduce new functionality like the pair step scaling factor, because here this is kind of like more or less it's just a snapshot of what it can do now. So you can basically change, because here you can see that the RMSD is not so great, so maybe there is an alternative, as I showed before. So maybe we can try BA05 as an alternative conformation. Here it might be a different situation. It also doesn't fit that well, but it might be well supported by the experimental data, and then like forcing conformation there. It might be really a unique conformation we cannot describe. So then there is a trick. You can just select like unassigned, and it means that it will not try to apply any restraints then on this step. And because obviously the population of classes are different, so sometimes it might be useful to apply a stronger restraints on a selected step. Because in this example, like we are multiplying the sigma, something like standard deviation of the distributions, and these by 1.5, and for this one it allows like tighter, so it will be stronger on this, trying harder to push it to BBO2. So you can like save it in like different sets, and each of them can be actually already, you can, by clicking this R, you can run the refinement on the server. But right now it's basically kind of tailored to this given problem, to this given structure. So this RefMac input we are using is not like really the most general version. But if you have some data and you would be interested to try it, let us know, and we will. Well, anyway, we will sooner or later derive a more general graphical interface where you can design your own input for RefMac and Phoenix and whatever, and either run it on our server or just download the restraint files and run it on your machines. So yeah, so as I said, if you find that DNATCO might be interesting, or even better, if you have some crystallographic or EM data and you would like to process that, let us know, and we are also open to feature suggestions. So I guess that's it now.
Okay, Jirka, thank you very much for the introduction of the DNATCO. And now this is a time for questions. So I don't see any yet, but I have one. So can we use this database for evaluation, for example, results of MD simulation of completely a new sequence of the DNA?
Yeah, sure. I mean, it's we write that if you have like a lot of trajectories, like a lot of data, it's probably not so good idea to just upload 1 terabyte of data there, and then for that I would suggest using the scripts, or even better, first contact us and let us reserve the resources for that. But it can work with any nucleic acid structure. So as I said, it uses Maxit to populate the missing things. So if you have like just simple coordinates, Maxit mostly can deal with it and convert it to a CIF and then like measure the torsions and so on. So it can be processed. The only issue is that sometimes from MD, force fields are not so perfect. So when it vibrates violently, some distances or angles might be like too weird, and then Maxit crashes because it's obviously designed for deposition of structure. So if you have CC bond 1.9 angstroms, it just shouts, this is not, like, you don't want to deposit that. So this we kind of inherited.
Okay. Is there any other question, either to the chat or you can speak out? If not, Jiří, thank you very much again. And we will not see each other next Friday, but 2 weeks. So have a good day and see you on the after Easter. Bye-bye.